In this video, I am going to discuss Stressen's matrix multiplication algorithm. Stressen's matrix multiplication algorithm is an advanced method for multiplying two matrices more efficiently than the standard traditional algorithm, which has a time complexity of big O of n cube. We all know that traditional matrix multiplication algorithm takes big O of n cube time complexity. Let's see the example. Before we discuss the pseudocode, let's move on to the example. First, let's see how the traditional algorithm works. Traditional matrix multiplication algorithm works. For example, there are two matrices A cross B. After multiplying, it would generate the resultant matrix, which is C. Imagine the size of each and every matrix is going to be 2 cross 2. If so, the answer, the resultant matrix also would, the size of resultant matrix also would be 2 cross 2. For instance, I am taking this example matrix A, B, C, D is going to be my A matrix, and my B matrix contains E, F, G, H. These two matrices I want to multiply. If you use the traditional method, traditional matrix multiplication method, this is how we would be performing the matrix multiplication. First row and first column, A into E plus B into G. So, in the first row, the first element would be this AE plus BG is going to be the first element. First row, second element is going to be AF and BJ. AF plus BH. Second row, first element would be second row, first column, which is CE plus DG and CF plus DH. This is how we would be performing the matrix multiplication. So, as usual, we would be just dividing the matrices. If you divide it, you would be getting the 4 different subproblems with n by 2 sizes. And here, if you check, in a traditional, normally, like as usual, we are performing the divide and conquer method only. This is one subproblem, B is going to be the another subproblem, C, D, each and every character here A, B, C, D, F, G, H is going to act as a different subproblem. If I apply the traditional matrix multiplication method, this is how it would get performed and the resultant matrix would be generated. So, here if you check to generate the resultant matrix, if you check, there are totally 8 number of multiplications we are performing. Here A star E, 1 multiplication, B star G 2 multiplication, then again star here 3, then again 4, 5, 6, 7, 8. So, totally in a traditional matrix multiplication, we are performing 8 number of multiplications and 4 number of additions we are performing. So, majorly we are performing multiplication operations and minimal number of addition operations also we are performing over here. Addition of two matrices would take big O of n square time, and for multiplication, like multiplication in the sense not normal multiplication or normal addition we are performing here when it comes to matrix multiplication, we would be performing matrix addition and matrix multiplication. Here if you check, the matrix size is 2 cross 2, so each and every subproblem would have only one element. Suppose if it is 6 cross 6 or 8 cross 8, each and every subproblem would have some n into n rows and n columns it would have. So, normally when it comes to multiplication, you would be performing matrix multiplication here, matrix addition here again the matrix multiplication only we would be performing. So, the complexity is normal multiplication matrix multiplication algorithm, the complexity is big O of n cube, and to perform the addition it is n square. Since we have used normal divide and conquer method here, that complexity can be derived only by framing the recurrence relation. If you write the recurrence relation for normal matrix multiplication using divide and conquer method, how many number of subproblems you are getting here? If you check, there are 8 subproblems you are solving, right? 1, 2, 3, 4, 5, 6, 7, 8. Totally there are 8 subproblems. So, 8 subproblems with the size of n by 2 each, plus other than multiplication we are performing addition also. To perform addition, the complexity is going to be big O of n square. If you solve this, if you apply Master's theorem and if you solve this recurrence relation, you would be getting the time complexity as big O of n cube. So, for the traditional method, traditional matrix multiplication method, the complexity which it is going to take is big O of n cube. Whether this complexity can be reduced using by applying some other technique, let's see how. Yes, it is possible with the help of Stressen's matrix multiplication. The number of the multiplications can be reduced, and obviously the complexity also would be reduced when you reduce the number of multiplications here. So, how this can be reduced using Stressen's matrix multiplication? Let's discuss now. Stressen's algorithm reduces the time complexity to approximately big O of n power 2.81. by using dividend conquer approach only with the help of the Stressen's matrix multiplication. When it comes to Stressen's matrix multiplication, just 7 formulas plays the major role here. Again, let us take one sample, 2 matrices we would take A cross B. A matrix has, as usual, A, B, C, D. This is my A matrix, and my B matrix has E, F, G, H. Let us apply Stressen's multiplication method. When it comes to Stressen's matrix multiplication method, as you did in the traditional matrix multiplication, you no need to perform 8 multiplications here, only 7 multiplications are enough. Let us see how. Just 7 formulas plays the very major role here. P1, P2, P3, P4, P5, P6 and P7. These are the 7 formulas playing important role here. There are 2 matrices. Imagine these are the 2 matrices which you want to multiply, and you will be generating the resultant matrix, which is C. How the 7 formulas can be applied and generate the resultant matrix? Let us check now. You have to remember these 7 formulas. To remember these 7 formulas, I will give you one shortcut here. Remember this word ahead. A alone, you just cut it off. Next step is, remember this word diagonal, then last column row, first column row. These 4 steps you just keep in your mind. Let us write the formula. First, remember this word ahead. A alone we are supposed to ignore. A, H, E, D. It has been written now. Next, if you are fetching something from the second matrix, which is from the B matrix, you are supposed to use the subtraction operator. If you are fetching any variable, any values from the A matrix, you are supposed to use the addition operator for the first 4 formulas alone. And also when you fetch it from the first matrix, you will be fetching it row wise. From the second matrix, you will be fetching it column wise. Okay. So for P1, the formula is A into, from the second matrix I want to fetch. So if you want to fetch something from the second matrix, fetch it column wise. Column wise, if I take F and H, and the operator which I am supposed to use is subtraction operator, because I am fetching it from the second matrix, B matrix. So for P1, the formula is A into F minus H. For P2, the formula is H into, now check the first matrix. If you want to fetch something from the first matrix, fetch it row wise and use the addition operator. So the formula is H into A plus B. For P3, the formula is, again take it from the first matrix only. Since I am taking it from the first matrix, take row wise and also use addition operator, which is C plus D. And for P4, fetch it from the second matrix. Second matrix means column wise we have to fetch it, right, and use a subtraction operator, but from G you are going to start, G minus E. Formula for P4 is. For P5, the formula is, imagine this word diagonal. So diagonally you are going to fetch the value from both the matrices. So diagonally if you take AD and EH is there, right. So only for the first 4 formulas this plus and minus operator is applicable. Here when it comes to for P5, 6 and 7, you can erase the previous rules and directly you can diagonally you can fetch the diagonal values here. The formula for P5 is A plus D into E plus H. And for, so these 2 steps we have applied, and for P6 apply this last column row technique. Last column from the first matrix, last row from the second matrix. Last column from the first matrix is, last column is B and D. So it's ulta, like for the first 4 formulas what we did means, if you are fetching something from the first matrix, we used a plus operator, and for the second matrix we use a minus operator. Here for the first matrix you are going to use a subtraction operator, for the second matrix you are going to use the plus operator. So last column is last column is BD, so write B minus D, and the last row from the second matrix is GH, write G plus H. So third step is also applied, and fourth step is first column and first row. First column from the first matrix, first row from the second matrix. First column from the first matrix is AC, A minus C ulta, right? For the last two formulas, in the place of plus operator, you are supposed to use the minus operator. In the place of minus, for the second matrix, you are going to use, instead of minus, you are going to use plus. Last column has been written from the first matrix is AC, first column from the first matrix, and first row from the second matrix. First column row, this is from the first matrix and this should be from the second matrix. First row from the second matrix is E and F. Instead of using subtraction operator, you are supposed to use plus operator, E and F. So this is the formula. So these 7 formulas we are supposed to remember. Only these 7 formulas plays the main role over here. So if you check in the 7 formulas, how many number of multiplications totally we are performing here? In P1, 1 multiplication. Each formula, only exactly one multiplication we are performing. So totally 7 formulas. So 7 multiplications only we are performing. And okay, after identifying the 7 formulas, using these 7 values, the resultant matrix can be generated. So to generate the resultant matrix, C11, C12, C21 and C22. So finally resultant matrix like this would be generated, right? Some value from C11, C12, C21 and CT2. This is going to be our resultant matrix, right? So to calculate the resultant matrix, the formula is for C11, P5 plus P4 minus P2 plus P6. This is the formula. And for C12, the formula is, if you add the value of P1 and P2, you will get C12 value. For C21, the formula is just add P3 and P4. For C22, the formula is P1 plus P5 minus P3 minus P7. That's it. So these are the formulas we are supposed to apply in Stressen's matrix multiplication algorithm. If you check, like it is not performing 8 multiplications here, only 7 multiplications it is getting performed here in the Stressen's matrix algorithm. Whereas in the traditional matrix multiplication algorithm using dividend conquer method, 8 multiplications got performed over there, but here only 7 multiplications. When it comes to addition and subtraction, there are more addition and subtraction operations are getting performed. More addition and subtraction operations are getting performed. But there only lesser number of addition got performed in the traditional matrix multiplication. Here more addition, comparatively when you compare the addition subtraction operation with the multiplication operation, addition and subtraction takes lesser time than the multiplication operation. So it does not matter here, like if you use more addition subtraction operation over here. So we reduce the number of multiplications getting performed here and increase the number of addition subtraction operations here, since it takes only lesser time complexity than the multiplication operation. So this is the formula. These are the formulas we are supposed to keep in your mind. Remember these steps, these formulas. Let's take one example and solve it clearly. So these are the formulas, Stressen's formulas, Stressen's multiplication formulas. Let's take one example. And solve it. One proper example. One simple example we will take. A matrix contains 1, 2, 3, 4. B matrix also contains 1, 2, 3, 4. Let's generate the resultant matrix. Divide the subproblem. If you divide it, you will get 4 different subproblems here in the A matrix, and again 4 different subproblems here in the B matrix again. And first subproblem is going to be named as A, and this is going to be B, and this is C, and this is D. And here this problem is E, F, G and H. Let's solve it using Stressen's matrix multiplication method. As I told you before, there are 7 formulas playing the major role. Let's write again all the 7 formulas for your convenience. A into F minus H into A plus B, E into C plus D, D into G minus E, A plus D into E plus H, B minus D into G plus H, A minus C into E plus F. And for C11, C12, C21 and C22, formulas of P5 plus P4 minus P2 plus P6, here P1 plus P2, here it is P3 plus P4, and here P1 plus P5 minus P3 minus P7. These are the formulas. Let's solve the example. P1 formula is A into F minus H. Here A value is 1, F value is 2 and H value is 4. So P1 value is going to be minus 2 and P2 value is H into A plus B. H value is 4, A value is 1 and B value is 2. So you would get 12 here for P2. For P3 formula is E into C plus D. E value is 1, C value is 3, D value is 4, so you would get 7 here. And P4 value is D into G minus E. D value is 4, G value is 3, E value is 1. When you multiply 3 minus 2, 3 minus 1 is 2, 4 into 2 is going to be 8. And for P5 formula is A plus D, E plus H. A value is 1, D value is 4, again E value is 1, H value is 4. So you would get 5 into 5, which is 25. And P6 formula is B minus D into G plus H. B minus D is 2 minus 4, G plus H is 3 plus 4. You would get minus 14 when you multiply it. And for P7, A minus C is 1 minus 3 and E plus F is 1 plus 2. So finally when you compute it, you would be getting the value minus 6. So we got all these 7 values, all 7 P values we got. Now we can compute the column values, the resultant matrix values one by one now. For C11, the formula is P5 plus P4. P5 is 25, P4 is 8 and P2 is 12. So minus P2, which is minus 12, and P6 value plus P6, P6 value is minus 14. If you compute, you would be getting the value 7. And for C12 formula is P1 plus P2, P1 is minus 2 and P2 is 12. So minus 2 plus 12, which is 10. And for C21 formula is P3 plus P4, P3 value is 7 and P4 value is 8. You would get finally 15. And for C22, P1 value is minus 2 and P5 is 25 and minus P3, P3 value is 7, so minus 7 and minus P7, P7 value is minus, already there is minus here, which would become plus now, plus 6. Now if you compute it, you would be getting 22. Now the resultant matrix C is going to be C11 is 7, C12 is 10, C21 is 15 and C22 is 22. So this is our resultant matrix for this: 7, 10, 15, 22. This is how the Stressen's matrix multiplication algorithm works. It is the easiest method. Only these 7 formulas we are supposed to remember. Based on these 7 values only, the resultant matrix values can be computed. So this is how it works. So if you check, A matrix size is 2 cross 2 and B matrix size is 2 cross 2. So the C matrix size also 2 cross 2. Suppose if it is 4 cross 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. This is one matrix which is 4 cross 4, A matrix, and B matrix size also is 4 cross 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 3, 4. This is our B matrix. Now how the Stressen's algorithm would work? Same formula only you are supposed to apply. The first thing is divide it into 4 parts. So now this 2 cross 2 matrix would act as A. Again this 2 cross 2 matrix would act as B, C, D, E, F, G, H. Apply the formula. For example, P1 formula is A into F minus H, right? So, A value is 1, 2, 1, 2 into F minus H, right? Where is F? This is my F problem, F sub problem. 1, 2, 3, 4 minus H. Where is H sub problem? 1, 2, 3, 4. Right? First perform normal matrix multiplication, matrix subtraction. If you perform, you will get some 2 cross 2 matrix here, and already there is A sub problem here, 2 cross 2 matrix. If you multiply these two, you would get final 2 cross 2 matrix over here. So, this is how it would get performed if matrix size is big. So, if it is even size, if it is multiples of 4, you can easily you can divide it, like you will be getting 2 cross 2 thing only. What if suppose you are getting odd sizes instead of getting even sizes? If you are getting odd sizes, for example 3 cross 3 matrix, if you are getting, if you get 3 cross 3 matrix like this, you can't divide the matrix equally, right? We are supposed to add 0 padding and then we should perform. Add 0 padding, make it even, and then apply Stressen's matrix algorithm, right? This is how Stressen's matrix algorithm works, only based on these formulas only. Let's see, let's discuss the time complexity analysis now. When you, since again we are using dividend concur method, here, we have to directly, we cannot trace the pseudocode, right? We have to frame the recurrence relation only. So, before I write the recurrence relation, let us discuss the pseudocode first. This is the pseudocode for Stressen's matrix multiplication. Function Stressen's multiply, there are two matrices A and B, n is the size of the matrix, and inside the matrix, if the matrix size is only 1, directly A and B can be multiplied, right? In A matrix has 2 and B matrix has 3, A cross B, which is very easy, right? So, directly it can be multiplied and the resultant matrix would be generated, right? Now, otherwise initialized matrices means in A matrix we will be getting 4 different subproblems A, B, C, D. In the B matrix again 4 different subproblems E, F, G, H you would be getting. So, after dividing it, after getting 8 subproblems, you are supposed to compute 7 formulas. P1 formula is what? A into F minus H. So, Stressen's multiply A into F minus H, right? So, I have written subtract of F minus H, and P2 formula is H into A plus B. P3 formula is E into C plus D. P4 formula is D into G minus E. Again, so only 7 multiplications we are performing, all the 7 formulas, and after getting all these 7 values, it's like the resultant matrix would be ready. Based on these 7 values, the resultant matrix can be computed. For C11, this is the formula. C2 formula is P1 plus P2. C21 formula is P3 plus P4, and C22 formula is P1 plus P5 minus P3 minus P7. Finally, after getting all, combine the submatrix into one matrix. Combine all this into one matrix. So, return combined matrices C11, 1, 2, C21, 2, 2. This is the pseudocode. Now, when it comes to time complexity analysis, since we have used dividend concur method here, no other go that we have to frame the recurrence relation and compute the time complexity. N is the size of the input, and if you check while writing the recurrence relation, each and every subproblem size is going to be n by 2, and only 7 subproblems, only these 7 formulas were playing the very big role, right? So, only 7 subproblems here. Based on these 7 subproblems only, the final resultant matrix was computed, right? So, it's going to be only 7. Instead of performing 8 multiplications, only 7 multiplications we are performing. So, 70 n by 2 plus, other than dividing it, we are performing addition and subtraction operation, right? So, this term 70 n by 2 term accounts for the 7 recursive multiplications of n by 2 into n by 2 submatrices. For big O of n square, this term accounts for the time spent on the addition and subtraction operations. when you solve this recurrence relation using Master's method, you would be getting the time complexity as theta of n log 7 base 2. So, finally you would get approximately n power 2.81. This is the complexity. Whereas, if you take the traditional method, it is big O of n cube. So, comparatively this Stressen's matrix multiplication takes lesser time complexity than the traditional method. So, Stressen's matrix multiplication, basically this algorithm reduces the complexity of matrix multiplication from big O of n cube to approximately big O of n power 2.81. This improvement is significant for the large matrices, making Stressen's algorithm a valuable tool in computational linear algebra and computer science, etc. So, however, it's worth noting that for smaller matrices, the overhead of the divide and conquer approach may not be the worth the savings in multiplication operations. So, Stressen's algorithm is most beneficial for large matrices. When it comes to advantages and disadvantages of the Stressen's algorithm, advantages are: one is reduced multiplications, as we all know. This significant reduction in the number of multiplications can make Stressen's algorithm much faster than traditional matrix multiplication for large matrices. And second one is time complexity, asymptotic improvement. For very large matrices, big O of n power 2.81 complexity provides a substantial improvement over big O of n cube. So, these two are the advantages. When it comes to disadvantages of Stressen's matrix algorithm, first one is overhead, which means the additional additions and subtractions introduce overhead, which may make Stressen's algorithm slower for small matrices compared to the traditional method. Second disadvantage is memory usage. The recursive nature of Stressen's algorithm requires additional memory to store intermediate matrices, which can be a disadvantage for very large matrices or systems with a limited memory. And third one is complexity of implementation. This Stressen's algorithm is more complex to implement correctly, especially handling edge cases when n is not a power of 2, as I told now. If it is not even sizes, if it is odd size, we have to make a zero padding and all, right. So, in such case, the Stressen's algorithm would be more complex when n is not a power of 2. So, in practice, for very large matrices, Stressen's algorithm would be used in combinations with other algorithms only, because it consumes more memory and there is a complexity of implementation. Thank you.